Okay, for people joining this live stream, we are looking at game theory design for Wolfram language. This is the second meeting in our recent series. We had discussed this several years ago, but now it looks like we are really getting this together and getting it ready for sort of full implementation in the system. So last time we had gone through some of this material, and we, I think, had discussed a bunch of kind of game equilibria, as I recall, but we were going on. Joseph, can you remind us where we got to?
Yes, so we were touching the replicator dynamics and also the learn strategies, and we were not discussing the coalitional games.
Okay, so let's just do a little bit of a refresher here. So the concept that we discussed previously was this concept of a game object. Although, you know, one thing that troubles me about that, there's a completely different meaning for the term game object, which may yet arise that is more like a game object in the sense of video games. And for example, if we look at, I mean, this is just a naming issue, but if we look at our things, I don't know what's going to be the future of this, but our, let's take a look here. Oh, why is that not coming up? Is Roger here? Can he perhaps address that?
I'm here, but I can't say why the search system doesn't work.
Actually, I'm using 12.3 here. Let me try using 12.2. It's always dangerous to use software from the future. Okay, let's take a look here. Do you know what the objects in UnityLink are called?
Game objects.
What's going on here? So this needs to be reported.
Yep.
This is really outrageous. I think I know what this is. I think it's because when the packlet hasn't been loaded, there's no evidence of its existence, which is just totally wrong. And I think we've been through this before, just totally wrong. Okay. Okay. Okay, so we've got things like Unity game object here.
Mm-hmm.
So unfortunately, there are different meanings of the word game. So is there a way to qualify what we mean by a game here, other than a game theory game, which is kind of a silly thing to say?
Yeah, well, matrix game can refer to matrix games.
No, I understand that, but is there a more generic term for a game theory game? I mean, it's a.
You can call it a theory game instead of a game theory game.
What did you say?
You can call it a theory game or a theoretical game.
Or maybe a finite game.
Game model.
Finite game wouldn't work because there's too many other things that are finite games.
Yeah. So I mean, possibly we're talking here. Let's see, where am I taking these notes? This is probably. Do I have a? Did I start taking notes last time? Well,
no.
Okay. Game model object, game. That seems more. Oh, there is an SW Notes 01. Maybe that's from the previous iteration of all of this work. Go ahead. Okay, so game model or game theory. Actually, another possibility is game theory object, which would make it very clear what it is.
Yeah, that's not bad at all.
There is but I'm not entirely sure how far we'll go in games. But these are finite games as opposed to infinite games. But
Yeah,
correctly, there are more than one meaning to finite.
I know.
But it's unlikely that the specification language generalized to infinite games.
I understand that. So, okay, so a possibility is something about a finite game, but I'm skeptical about it. Maybe that will work.
Yeah, maybe not. Maybe the other ones are having a prefix. That's how we often done. The common case is short. The
Which
less common
case?
Like plot is short, list plot is longer.
Yeah. So
okay?
what are you
It could have been
here?
function plot and plot.
Sure. But so what is your point here?
Yeah. So maybe we'll come to that when we add it later on.
Come to add what?
If we add infinite games, differential games,
yeah.
maybe they get a longer name.
Yeah, I understand. That makes perfect sense. But the question then is, I just don't think game object just doesn't seem like the right thing, because it's too close to what we're dealing with in okay, we got game theory model is also possible. How does the game theory model thing agree with the way we use model in statistics and potentially in other areas?
They're related, but not particularly close. There are many uses of model. We have optimization models too, but we don't call them models.
Yes.
In statistics, we don't call them, only regression ones are called models. The distributions are models, but we don't call them models.
I know, we call them distribution.
And the processes are also models, but we don't call them models.
Fair enough. Okay. Let's just review, though, how this is supposed to work here. So I think we agreed last time. So we've primarily got these matrices, right? But we also agreed that we need the possibility of having associations there so that you can name the actions. Is that right?
Yes.
Okay.
Yes.
That's not reflected here, though.
No. In the end, I try to address some questions from the previous meeting.
All right. Okay.
But otherwise, this is more or less the same what was previously.
So this, I didn't even know we really had these. I mean, how many of these do we have? Do we have these for other games? I mean, if I look at
yeah, I found it only for tic-tac-toe. But
I don't even know what this means for tic-tac-toe. I mean, it seems like I don't understand this. I mean, the tic-tac-toe game tree is 4,000 elements, so I don't understand what this is.
I'm not sure. But,
it's trying to use the symmetry to reduce the number of distinct moves.
I see. Okay, that's kind of interesting in its way. Okay. So what we've got here then, as I understand it, I'm just trying to remember how this all works. You've got this. Okay, so what's the idea with all of these? Do we have a summary now of all these various functions that you're proposing or not?
Yes, in the end, I try to reduce the number of functions to 5.
All right, here we go.
So in the end, there is these essential objects and functions.
Okay, but so then here, this first thing, okay, is all the same creature. That first thing is all the same, right? This thing here, right? They're all packaged together in the same object, correct?
Well, it could be. However, there are some things like, for example, the coalitional games, which could be under the same game object, but if there is a possibility, then I would separate them.
Well, we'll have to figure out the detailed design, right? So,
yes.
So I mean, the generic case. Go ahead.
I say we haven't talked about all the complications of coalitional game right now. I think it would be nice if you could fit them in, but I can see that it would be challenging to fit them in, and they might have to have their own object type. But
okay, so then from game, we're looking at, from this game model or game object or whatever it's called, we're then I mean, it's possible. Look, it's possible that we could get away with, as Roger is kind of implicitly suggesting, calling this collection of things finite game. And that would distinguish us from the game object in the sense of video game. And allow us the possibility of having different structures for example, infinite games in the future.
Yes, infinite or continuous or differential, those are all relevant possibilities.
So what would it be? Differential or differentiable? Or continuous, otherwise known as a continuous game. Is finite game also discrete game?
Yeah.
Yes.
Discrete, it might be even better name, actually. Oh, maybe not.
I'm just worried about things which are in the set of finite game or discrete game, which are not really included here because they're just, yeah, they're you wouldn't try to address them with this formalism. You're not going to try to put go in this, for example.
Right.
Those
well,
are finite discrete games, but
okay. But so, what is the characteristic of? I mean, these games have the characteristic that they're modeled with matrices and things. Is that true?
Yes. So
Yes.
here, there is a finite number of players, and every player has a finite number of possible actions.
Well, so is the right name just matrix game? Or does that not capture some of the types of games that people would consider here?
I think some games are more naturally represented in a game tree form, because if you try to transform it to a matrix form, then they are too big. So it's better to represent them in a tree structure.
Well, so conceivably, we would have two cases then. We could have game tree and matrix game.
right. And right now, those are separate things under the game function.
I see it, right. So, I mean, but what I'm thinking is, if you have a matrix game and you say game tree of that, it would convert it to the tree form and give you visualizations appropriate for that. Does that make sense?
Yes, but it's more natural to go from game tree to matrix game. From
well, fine, but
from
I
matrix
understand.
game, it's not unique, and also computationally, it can be very demanding
to do what?
To find an appropriate game tree representation of a matrix game.
Why?
Why? Well, you can always find one, but there are very much there is non-uniqueness in that.
I see. So it's not an equivalent representation. So you can't take.
No, the tree form is a richer representation in this from this point of view.
And there's no obvious default from a given matrix game for its tree form.
No. There is a theorem that every matrix game can be represented by an incomplete informational game tree, but there is no canonical rewriting.
Okay, all right, I understand. Okay, so let's keep going here. So then this stuff, what is the representation of the equilibrium? How do you, given that you have let's say a matrix game object, how do you represent the equilibrium then?
So in this initial implementation, the equilibrium is simply a set of strategies, which is a probability distribution on the actions for every player. So
okay, but how do you represent that?
Well, here are represented with nested lists, which simply give back probabilities, which are positive numbers summing to 1.
I see. So in other words, whatever the original. Okay, hold on. I'm confused here. There's a matrix, and then there's a state. There's a matrix representing the various payoffs in the game, and then there's some particular state which is the solution to the game. Like there's a matrix and a vector, in linear algebra. Is that correct?
Well, if you have n players and those have strategies, then the equilibrium strategy for Nash equilibrium is a set of probability distributions, a set of mixed strategies on every action set.
I understand, but the dimensionality, the game is, if I'm understanding, is the outer product of the strategies, the payoffs.
It's players and choices, but with probabilities attached to each to handle the mixed strategy case, right? So you don't just have the option of playing A or B. You have the option of playing A with probability 0.67 and B with probability 0.33.
Okay, so how does that relate to our categorical distribution stuff? Roger, or anybody else?
Well, it's pretty much a categorical distribution.
Okay. So, Joseph, you know what we're talking about there?
Not precisely, no.
Okay, so
we'll go through that, but it's...
Yeah, I mean, there's this function categorical distribution, which represents exactly what you were just describing. That is, and that would give you a natural way when you get to the differentiable games, that would give you a natural way to generalize this, right? So this is a categorical distribution which allows you to specify probabilities for different categorical outcomes.
You could call them strategies or actions in the case of games.
Right. But the point is that, I mean, what we're using, and I have to say, this name categorical distribution is starting to concern me, because the places we're using it, it's just a very bizarre, complicated name. Right? I mean, it's really more like a choice distribution or something like this. Categorical is awfully weird. I mean, we're using it in quantum mechanics for outcomes of quantum experiments. We're using it here. We're now thinking about using it here for strategies. What would you think about this being called choice distribution? Roger?
That's a it would be uncommon, but it's not wrong.
I know, but the point is that we're using it more generally than just for statistics wonks. You see what I'm saying?
Mm-hmm. Yeah.
I mean, we're going to end up using it for, by the time it's being used in quantum mechanics, and particularly in like categorical quantum mechanics, where the name categorical means something utterly, utterly different, right? We know we're in bad shape.
Mm-hmm.
I mean, it's still
it's also not inconceivable that we have a few variants of this that's sort of tuned.
Yes, I agree.
To see what I'm saying?
Yeah, so long as they interconvert properly.
Exactly, as long as they do that. But it could be that there are input methods and other things that are more tuned and makes it perfect for some.
Right. But so this, in what you're saying, I have some state. So here.
Sorry, Stephen, we should think about state differently, because there are games with intermediate states before their payoff outcomes. These games don't have an internal state. We're only looking in the solution space of strategies, so it's not really a game state in that sense. It's just
yes.
Yeah. So this is usually referred to as a strategy.
I understand, but okay. So do you have right now the explicit form? Because I mean, we're not going to have all of these. At least I don't think we're going to have. Although I mean, I could be convinced otherwise. These kind of special game heads.
Mm-hmm.
I mean, I don't know. Does Roger have an opinion about that? I don't know this field well enough to know whether it makes sense.
I don't know. I want us to make it easy, and we want a big collection of those so you can get all the standard games. Exactly how we do that, I haven't really thought it through yet.
Changing strategies. I think it would be cleaner if these are method option kind of things, rather than different heads.
No.
We're probably not talking about the same thing.
No, we're talking about here, if there is a different way to specify a Bayesian game and to specify. I just don't know. Is the input
I thought you
form
meant
for
things like tic-tac-toe.
No, I didn't mean anything. I was talking about Bayesian games as opposed to perfect information games.
I see.
The question is whether or not you want to have the information parameters of the game be something which is a different head, or it's just an option.
Okay.
I
think we have to look at sort of
within.
Yeah. I think Bayesian is a very strange name for it too.
Joseph, can you comment on that? I can't comment on this.
Well, yes. So Bayesian game is a standard thing. It's a textbook name for it. But for the previous question, I think the Bayesian games, the matrix games, and also in some extent the game trees can be packed together into one object. So previously, Steven said that, for example, interpolate functions can have different inner
Yes.
life, and in following that reasoning, a game object can have different inner self. So it can be a matrix game, a tree game, or a Bayesian game.
In its representation.
Yes. But I mean, a Bayesian game has no one unique matrix representation. It's a different thing. But if we want to minimize the object, what we use, then it more or less it fits into the game or the finite game category. To define a Bayesian game, you need to specify more things, and you also need to add a prior on this and that. We can go into that, but you need to specify more things to define a Bayesian game.
Okay. I found that this area is very much like a Russian novel. Like everybody has 3 names. You know, that there are lots of names, textbook names. There's not just one. There's like lots of textbook names.
Yeah, that's always complicated in terms of our naming efforts.
Yeah.
All right, let's keep going. I think you'd wanted to talk about different types of games here. Let's see, you would want to talk about replicator dynamics, which I don't understand what it is. So
yes,
where is the name? First of all, does replicator dynamics come from people doing kind of biology inspired games, or what?
Yes, so it's a sub branch of evolutionary game theory.
Okay, fine. Then I think I know it's history. Okay, fine. I have no idea. You know, these things could come up in, I don't know what, you know, legal negotiation or something, and it means something utterly different. But
no, this is a standard thing, and yeah, so this is in the intersection of biology and game theory. Here, basically, you define a fitness function. So you imagine that you have some kind of population, which means that in this population, different players or different replicators follow different strategies. Let's say different pure strategies. If they are selected to be player 1, then they always defect, for example, if we are talking about prisoners still. Yes. And the other species is always cooperating, for example. And then you can ask that if you start to play, if one kind of replicator, one kind of strategy starts to play this game in the given population, then what will be the expected utility, the expected gain? And based on that expected utility, this is what you take as a fitness. And as a function of that fitness, it will replicate or shrink in numbers. So there is
hold on. So is this happening in continuous time?
Yes.
Okay, so one thing we can imagine is an iterated game happening in discrete time where there are, you know, rounds of the game and yes, people have different strategies. Okay.
Yes.
Which can depend on the history. So in this case, this is
this is a continuous
information.
Yes.
So this is definitely the continuum limit of that idealization, that the populations are playing against each other in exactly even groups. There's no probabilistic pairing, right? And there's no discrete steps. So it's a continuum limit of everybody's playing everybody else.
So this is the SIR model story of which you presumably could. Can you in fact get? I mean, is there a version of a replicator dynamics game that is the SIR model of epidemiology?
I didn't see, but I think it's not. I think it can be constructed.
Okay, but so essentially, what this is doing is it's generating a bunch of ODEs. What otherwise would be discrete matrix operations become a bunch of ODEs here.
Yes.
Exactly. And just one confusion that I have here is, okay, so there's something dot. There's some variable, the time derivative, and that's what's being set equal to the game outcome. Is that correct? Is the rate of change is set equal to some kind of game outcome, or what?
Yes, game outcome given the proportions in the population. Yes.
Yeah. So basically, for a given species or a subpopulation with a particular strategy, they're going to get an average fitness with this state of the background population, and the fitness they got in terms of the score they got playing everybody else determines their rate of replication, right?
So is this related to population dynamics?
Yes, exactly.
Yes, this is population dynamics on strategy.
Okay, so those exist both in discrete time and continuous time.
Well, absolutely. It's a logistic map. In discrete time, this would be things like the logistic map.
Yes.
Which game theory is not well equipped to deal with, as I understand it. Or is that, I mean, people have done this. I know people do this with cellular automata and things. Yeah, go ahead.
You could definitely do this with discrete form, where you're just doing the game evolve list versions of it, where you're just doing discrete steps and picking the pairings randomly or some other way like that from step to step. There certainly are discrete versions of this, especially in spatial form, but even in non-spatial form, you can have a discrete version of this.
Okay, but so I understand that. I mean, so
is all population dynamics replicator dynamics, or is it some?
I think this is most of evolutionary game theory is modeled in this way. Is that not correct?
Yes, there is a zoo of different replicator dynamics. This is the default, what I implemented here. There are discrete, there are some with some stochastic. So there is somewhere there diffusions between strategies. There are some which try to damp down the oscillations, what probably you will see if you scroll down, etc. So there is a whole zoo of that. But I think why it is nice to implement those is because it gives a time horizon of equilibria, and also.
But for instance, could you take a food web and simulate its dynamics?
If you're doing it at the level of ODEs, yes.
Yes, certainly.
But I mean, I don't think
this is definitely used in ecology models generally, right? Including spatial ecology models.
But spatial is yet different again, because then it's like people do, cellular automata with continuous variables and things in that case. But then that's a whole, look, Roger, this is very similar to the, system model stuff in engineering. Right, it's a bunch of ODEs, and this is
no, of course, yeah. No, I recognize. I'm just trying to delineate what this is, because I have a whole, I have a yard on population dynamics. It's not a small area.
Right. Right. So the answer, I think, is this: there are a class of models that are pure ODEs, and perhaps there's even a subset of those models. I'm not sure, but I think there's a class of sort of everybody mixes with everybody ODE models. That's what this is covering. And I think all of the verbiage of evolutionarily stable strategies and so on, which presumably is one of the things that game solves should be able to produce. Is that correct? Or did I misunderstand?
Yes. So yes.
It somehow reminds me of systems biology as well.
Well, less so, I think. I mean, this is more the ecology story. Well, I see what you're saying, but where you're actually computing. Well, that's so closer to system modeling, where you're actually getting ODEs that represent chemical processes and so on.
Mm-hmm.
But so in this case, okay, so the point here, I mean, I'm a little bit concerned that this is a bit of shoehorning of a derivative being set equal to, the ordinary game case is you're specifying a strategy and you just get a definite result. Here, you're getting the result is a time derivative that you're then putting in and then solving the ODE with that time derivative, if I'm not mistaken. I mean, there's basically a model construction method for systems of ODEs for things like ecology. Is that a true statement? Where the story that you tell, so I mean, the microscopic story you tell is one of individual games being played with certain outcomes.
Yes.
The reason this ties back to game theory in other ways besides that is that the particular populations you define here are often differentiated by their strategy in a game space. So like you can have these things evolving where, in Iterated Prisoner's Dilemma, one of the subpopulations is things following the tit for tat strategy, right? So the particular strategies they're following are the things that then have evolutionary dynamics and evolutionary fitnesses and take over the system or don't take over the system. And that's the kind of stuff you're exploring. The point is that the selection is on something which is defined by a game strategy.
Yes. I mean, to me, I have to say, my gut feeling is that this is not the same underlying function as that what you would be doing is to say, yes, you might have a, whatever we're calling it, a matrix game, for example, but then this is some wrapper around that's the underlying kernel, but then this replicator dynamics thing is a separate is something that uses that kernel, but uses it in a different way than, for example, GameSolve uses that kernel.
Yes, exactly.
That's correct. That's correct.
Okay.
And there's going to be things like that, which are, the replicator dynamics can be different. The population mixing can be different. Any spatial thing can be different, right? There's a couple things, there's things which are typically done on top of that kernel. But
okay,
you're right,
fine.
they're all independent of the kernel.
I see. So we've got this notion then of, we've got yet another potential name for this concept is like a game kernel, which then, well, I don't know if that's the right name for it, but I noticed somebody on the live stream, I see, commenting on whether this is related to why I was I put out a strange tweet about the fact that I put my collection of economics books on top shelves, which has made them 20 years ago, which has made them extremely hard to access. Asking whether this is the reason I was looking at those. No, it isn't. That has to do with much more foundational questions in economics that I've been curious about and making progress with, I should say. But that has, so far as I know, although it's a good question to raise, so far as I know, it has nothing to do with this, although it's actually a good question to raise. Okay, in any case, all right, so the replicator dynamics takes one of these kernels and gives then what? Interpolating functions or what as the output?
Yes. So these are the solutions of ND-solve functions. This is the appropriately nested list of interpolating functions.
And to be clear, you should have one of those interpolating functions for each subpopulation. Here, the subpopulations are pure strategies, but they don't have to be. The populations can be defined in different ways. But
so in other words, what you're saying, in the previous case, it might be a choice distribution is the output for a given player's behavior, so to speak. In this case, the output is an interpolating function. Is that correct?
Yes. And in many cases, the fixed point of the game solve can give you many possible solutions, and these replicator dynamics usually or often has a fixed point, and depending on the initial conditions, the fixed point will be usually one of the solutions of game solve.
In other words, I don't understand the time dependence.
The asymptotics of this could be the same as the Nash equilibrium.
I see. Then it goes to a fixed point.
Yeah.
Yes.
Which these ones are not.
Yes,
No.
these ones are oscillating, and as I mentioned, there are other replicator dynamics equations which tries to damp down these oscillations and find. I mean, if you would start from the equilibrium, the dynamics wouldn't go out from there.
So, I mean, for example, just so I understand for context, the Lotka-Volterra equations are an example of this replicated dynamics or not?
If I'm correct, in the Lotka-Volterra, you are not calculating proportions, but absolute numbers. But if you convert the absolute numbers to proportions, then yes.
And so what is the strategy? What is the kernel of the Lotka-Volterra equations in this sense? You know, fox eats rabbit or something, or and then what does that mean in terms of a strategy here?
I mean, so in the case of rock, paper, scissors, for example, it's just one is beating another, right? So you can have similar relationships among your different species in a Lotka-Volterra situation. So if A interacts with B, you have a deterministic outcome, and one is a positive, one is a negative utility, and if those are always +1 and -1, you would get something like this.
Okay, all right, fine. But so then the wrapper that we need.
So Jason, here I noticed that you say utility, and Joseph says payoff. So that's another one of those two names occurring repeatedly in the literature.
Yes, technically the payoff is for a particular set of choices, and for the utility is an expectation of that across your mixed strategy. So if you're sometimes playing this and sometimes saying that, you're sometimes getting this payoff and sometimes getting that payoff, and the expectation of the two of them is your utility. And yeah, there are subtle distinctions like that when you're talking about one move or one shot of the game, or when you're talking about an expectation.
Yeah. Here, I think utility is more precise. So utility is something what is expected that the players want to maximize. So the players want to maximize the expectation of utility, and the payoff, that it can be monetary or something, and this is not always equivalent to utility. So maybe you want to maximize the logarithm of your monetary reward, and in that case you need to transform the monetary payoffs to utility, and then you can apply game theory.
Yeah, that's fair. Especially in economic context, you'll have a mapping from payoff to utility independent of the expectation.
So I'm confused about something else. So in one case, you say there's a choice distribution, certain probabilities for different strategies, right? Is it the case that here, when you have this continuous value in the replicator case, then instead of having a probability, you instead have just these continuous valued outcomes varying with time?
These vertical axes here are the population. This is population strategy portion of.
I understand. Right.
Population values in that strategy. These strategies, I think, right here are currently fixed ones, not mixed ones. You can also have this where you have mixed strategies, and the thing which is evolving is what probabilities you put on things. Those are different things, right? Here, you're just changing the concentration of the people following strategy A versus strategy B, where those are.
So do we get stochastic differential equations then?
Hold on, let me just unwrap this. So, I mean, what you're saying here is this is sort of a frequentist interpretation of the choice distribution. Is that correct? I mean, we could as well have said there are different probabilities. I mean, there's two things going on here. One is the continuous variation with time. The other is that we are representing, if I'm not mistaken, you know, these are the probability parameters in the choice distribution presented as the frequency of different critters as a function of time. Is that correct?
Yes, I think yes. I mean, here in this situation, you don't assume that the players can play mixed strategies. In this situation, you think that the players or the replicators are using always the same pure strategy, and only their proportion in the population can vary.
No, I understand. But so the generalization of this would be, okay, so we've got two different.
Sorry, just quick. There's a way in what you were saying is right, Stephen, in the sense that as these populations fly around, the strategy you're going to face is changing because you're facing a population that has a different set of strategies in it, which is the same as facing an opponent with that point in the mixed strategy space, right? So, but you're still keeping your strategy fixed in each of these cases. So the evolutionary pressure is on the guy with this fixed strategy, but it's like he's playing against, because he's playing against the whole population. It's like he's playing against a mixed strategy opponent with different changing mixed strategies.
So one could imagine another case where in the choice distribution, the values of the probabilities are interpolating functions. Or put the other way around, there's an interpolating function that returns choice distributions. That would be a mixed strategy as a function of time. Does that make sense?
Yeah, I mean, you'd have to specify what the at that point, the populations that you're having evolutionary pressures on are a continuous distribution kind of set rather than a
I get it.
Point set.
Right, but that would be the case if you were putting pressure on their probabilities, which are continuous.
In which case you get stochastic differential equations.
One would assume. Right. Okay, but so that's the
other. You also can get the stochastic case if you let the pairings be instead of being pairings against the expectation of the whole population. If you let the pairings be random choices of who you're meeting out of the population, you'll get a stochastic dynamic then too.
All right. Look, my takeaway from this is point one, replicator dynamics is a separate wrapper around these kernels. Point two, we need to think carefully about what the representation of these, things we're considering outcomes, where by outcome, I mean in general, even something like this interpolating function is a function of time. Because I mean, game solve is always just giving us one result, correct? Although I don't know what happens in the iterated case.
So in game solve, you can get a lot of different equilibria.
I understand, but it's each one just sits there. I mean, it's not something where there's a time series, for example.
No, that there is no time dependence there.
Right. Yeah. Whereas an iterated game, there would be a time series.
Yes, and also you need to specify an initial condition. So this is another extra feature here.
Okay, which one should we look at next? Should we look at learn strategy?
Yeah, we touched learn strategy. These are basically approximative solutions for games. We touched those. I think this can be implemented in game solve. I mean, you can ask for.
So it's less like a Newton approximation or something, except it's not Newton, it's something different.
Yes.
The one thing that we have to leave some room for here is the possibility of some of this, plugging in more general algorithms. We talked a little bit last time about this, being able to plug into some of the machine learning framework stuff or some of the net chain stuff and so forth. Because people are definitely interested in whether or not they can have like just typical online learning strategies and drop one of them into this. So we don't want to have anything in the game solve stuff that puts that so deep inside that people can't have sort of kernel-like control over what adaptive algorithm they want to try it with.
Well, so presumably what happens is there is a I don't know what it's called. It's a game iteration function or something inside game solve. Or game, I don't know whether it's game solution function, game iteration function, whatever, where it's being given. I mean, what will be the analog of that in, for example, one of our iterative minimization things, Roger?
Well, we've packaged that all down at the method level.
Yeah, right. For most things.
Because
But here, what we want to be able to do is to expose the thing on which you essentially do a single gameplay or something. If we're doing, well, I'm not sure how that quite works.
So there's two separate things. One is you might want to have the game evolve kind of thing of doing discrete trajectories of it, but the other is you do want to have something like method-like control over anything that's a learned strategy. I think those are two different ends of the spectrum. One, you want to be able to just do something more explicitly, just give me a single trajectory, evolve this, and the other is you want to be able to specify your learned strategy algorithm to use this or that function or adaptation method fashion.
Ethan on our live stream is commenting that NetTrain should be able to learn policies. Yeah, wrong team to talk about that in. But I mean, we're talking here about, I would assume, the analog of a net train policy being able to be at least supplied, if not learnt. Okay, let's yeah, commenter, game repository. Yes, we're talking about that. In other words, to be able to have named games, of which Prison's Dilemma and
Yes,
these things are. I think we talked about that last time.
Yes, and they are listed in the end of this.
Okay, all right, fine. Coalitional games. What on earth are these?
Yes,
did we talk about these last time?
No. This is where we stopped. And so this is also usually treated under game theory, but it's a very different concept, I think. In this case, you can imagine that there are some players and they can form coalitions. And the question is that how much gain they can earn if they are in this coalition or in that coalition. So basically, the mathematical structure of a coalitional game is what I would say a measure, which associates real numbers to subsets of a given player set. So
Wait a minute. So they're mixing strategies from different players, or
they're getting to do strategic cooperation with each other. Where I'll play this strategy if you play that strategy, and then the payoffs we each get, we get to share among ourselves.
I see.
Yes.
So we get to make side payments to each other within our coalition in order to coordinate our strategies and try to get a better outcome for our joint set at the expense of the other players of the game that aren't in our coalition.
So
yeah, here
So the other thing, like before, Stephen, we modeled individuals. Here we modeled groups. So the other ones are called non-cooperative or non-coalitional.
I see. Cooperative games I've heard of. I just haven't heard of coalitional games.
I think it's the same.
Yes, this is the same.
Okay, but so in that case, we need some representation for one of these coalitions that has, if I'm not mistaken. So previously it's like saying we've got labels of a vector that are dimensions 1, 2, 3, but this is now a combination of those dimensions. Is that right?
Yeah, so basically a possible coalition is a subset of players, and that's it.
It's not weighted. The subset is not weighted.
No.
I see.
But each of them they also have a strategy or strategies that they're agreeing on. So the player is, the coalition set is just the set of players that group, and then, but the rest of the specification, what the coalition is what strategy they're all following and how they're dividing their joint payoff.
So mathematically and axiomatically, so a coalitional game is really just a set function, which associates real numbers to subsets. And then you are right that you can generate coalitional games from non-cooperative games, but I mean there are separate modes how you can do that. But in the end, this measure, this coalitional game, this set function is a separate entity and a separate object, and then you can manipulate that and analyze that without any reference to the original game.
So what is your proposed design for this?
So here I would say that there can be a coalitional game object, which contains a set function, which associates real number to subsets, and the set of players. If you scroll down a little bit to, yes, a little down. So here is, for example, here is this CG3, for example. This is something what I used as a coalitional game. There is, in the end, there is the set of players 1, 2, 3, and there is a set function. Here there are Shapley values. If you scroll a little down, then I gave some a little more. I gave some visual.
Okay, so this is a post set. This is a representation of a post set.
Yes, and here
That
the size of the circles are proportional to the payoffs of the coalition.
I see. So if everybody gets together, they have the biggest payoff in this case.
Yes. Yes.
So wait a minute. So for a given set of strategies, you can make one of these kind of weighted Hasse diagrams to represent what people will be getting in each of their different subsets.
Yes.
Is that true?
Yes. So there are different ways how you can construct. For example, a standard one is this alpha optimal. That means that, let's say you form a coalition and then you assume that everybody is against you. Everybody is against your coalition. So what is the minimal payoff? What you can gain if you join forces into that coalition? You can ask this question and then associate this answer for every subset. And that's how you can define, for example, a coalitional game derived from a multiplayer game.
Okay. So, I mean, one thing, I mean, it's quite a separate thing, but I mean, the visualization of these post sets is something that seems to come up multiple times. It probably deserves its own approach. But
so I didn't see this visualization anywhere else. I just thought that it could be nice to do that, or maybe intuitive, more intuitive. What other methods
I used this actually bizarrely in the thing that I did about the empirical metamathematics of Euclid recently. I used exactly the same visualization idea.
Yes, I mean for coalitional games. I didn't see
yeah,
any
right.
literature, something like that. Usually, if you scroll a little up, usually people are using these subs, so these other forms. This is something what's happening if you have 3 players. Then the natural question is that if everybody is joining in the grand coalition, that's okay that they earn a lot of money or something, some transferable utility, but how do you want to divide those utilities between players? And this is the main question in coalitional games. The blue area represents for the core, which is a kind of division where nobody thinks that if he or she would go out from the coalition would get a better position.
I see.
And the blue dot is the Shapley value, and there are other many concepts about that. The problem is that if you have 3 members, then it's simple like this. If you have 4, then this is in 3 dimensions. And if you have more players, then the dimensionality of these objects grow, and it's very hard to visualize.
But I mean, in a sense, this is a similar thing. You know, when you have these regions, Roger, how does this compare to like solutions to linear programming problems and things like that? In other words, the way that we'd specify, I don't even know how we specify that. I mean, if you have some complicated simplex thingy, okay, maybe I'm.
But first of all, we have a simplex in any dimension, and this is just a simplex then.
Yes.
Right.
But the linear programming, I mean, any optimization, you get the optimum value, and you get the optimum argument, the location where that value is attained.
Right. The argmax or whatever.
Yes.
But I mean, so your nucleolus thing, whatever that thing is, I don't know what that is. What this region here where everybody should be friends type thing, that presumably is described by a set of inequalities.
Yes.
Is that true?
Yes.
And so.
Yes. And the fortunate thing is that the linearity is not ruined if you have more players. So in every dimension, this will be actually a polygon. Yeah.
So in other words, the thing that this could potentially return is, I mean, we don't have a packaged collection of inequalities. It's just a list of inequalities for us, right, Roger?
Yeah. I mean, logical combination of inequalities is the most general.
Right. So that would be how we would return this thing. And in some sense, this is.
But is it? I didn't hear that. Is it always linear?
Joseph said yes.
Yes.
but I mean, and then to actually get this picture, you're doing what? A region plot? How do you want the region that satisfies all those inequalities?
Well, actually, some of these questions are answered already in this transferable utility package, what is already implemented in Mathematica. There is this link for that, this TU games.
Okay.
I had no time to merge this with that, but there are many functionalities already.
Cool. Okay, that's nice. Wow, and this is
written by an author who has a similar book on the topic. So
cool. Okay,
yes.
I'll be in touch with this person. But this is a very old. Oh, created 2005. Maybe from an even earlier thing.
If you see this PDF, for example, then you see some examples. There is this 2 games.
Okay, well, it seems like you should be in contact with that person, and all right, but let's go down. We're going to run out of time here, but let's look a little bit at iterated games. Yes. Is that our last big topic here?
Yes, this is the last topic.
Oh boy. Okay. 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 So let's try to understand this.
Okay.
So as I understand, I mean, when I've tried to understand this in the past, at a given moment, a given player could have is applying a function to the complete history of all previous gameplays. Correct. Is that not correct?
Okay. Yes, correct. This is a behavior strategy with perfect recall.
Okay. But so in general, it's just a function that gets applied to all previous results, whatever that means.
Correct.
And again, let's understand, how does this relate to the whole kind of reinforcement learning story and so on? Do we understand that? I mean, in a sense, that's building up, you know, as the robot pokes around the world, trying different things, it is effectively building up a model of what's going to happen in different cases, which I think is the same type of thing as you're trying to do here, if I'm not mistaken.
Well, I think this is a restricted version of a behavior strategy. So in this behavior strategy, you can assume that you know all the possible moves for you and all the possible moves for your opponents as well. And based on that, you can construct the function. If the game is very complicated and maybe the action sets are too big, then maybe you don't assume that. You only take into account in the past what kind of payoffs you get or what kind of rewards you get, and only. So I'm not an expert, but you try to find the optimum between exploration and exploitation, and do those kind of things. So
but I mean, but I mean, so for example, iterated prisoner's dilemma, sort of standard case. Yes. You know, one of the things. So I know, you know, the Bob Axelrod's experiments, for example, where he's looking at different possible strategies that can be, and I always thought that was kind of a hokey thing because, you know, in my world, at least, you can actually enumerate explicitly different possible programs to apply. And I don't know what's the measure on the space of programs, on the space of strategies or something. And if you are looking at, I mean, I don't really understand how you can make statements about, okay, how do you typically parameterize these strategies? Because I mean, the parameterization that says you get a bunch of random students, I don't know why it isn't professors, but to you know, to program up various strategies and see who wins type thing, seems like a, you know, in a world, at least the one that I'm used to, where you can start enumerating all possible programs. I mean, I think I did an example of this sometime, but my question is, how do people typically parameterize these strategies?
Well, I think there are some strategies which have parameters, usually, which maybe you can say that, okay, the simplest one is that regardless of the history, it uses a random strategy, for example, or even a pure strategy. That's the simplest one. Then you can say that it looks back 1, or it looks back 2. In that case, you can parameterize this by Markov chains. But in practice, what happened in these tournaments, for example, and there is a Python package for XRO tournaments, there you have named strategies around.
Okay, I think that's crazy. I mean, honestly, I'm sorry. I think that's, I'm amazed that people haven't done this better by now. I mean, this was a trivial experiment that I did once, where this is playing, using cellular automata as strategies, right? And at least there, it's not a question of named strategies or ones programmed by some random group of students. It's you can actually enumerate possible algorithmic things.
And this has certainly been done with looking at all the possibilities, and there's even result, like if you look at the simplest one look back only things that rules that are in a sense dumber than tit for tat work better than tit for tat, and so on.
Okay, fine.
The person who's done the most on this, I think, is Martin Novak at Harvard in the Center for Evolutionary Dynamics.
Right.
He's done a lot of spatial game theory, but
I know, yeah, right. Yeah, I know him. Although he's unfortunately in retreat right now, but
So here, so what I proposed here is that if you have a game which you can take as a game kernel, for example, and you enumerate a finite set of behavior strategies, which is exactly a function taking the game history, and also you need to specify here who are you, so which player are you, then they can compete, they can play with each other, and then basically this set of behavior strategies and the game kernel can generate a new payoff structure and see what would happen, for example, if TFT was playing against TFT, if random was playing against random, etc., etc. But it's up to you what kind of behavior strategies you list.
Right. So the basic point is we have to be able to feed into a strategy as a function. We have to have a nice, clean way to specify the state of the world for that function.
Yes.
Right. And then that function, then essentially what we're providing here is the analog of nest list.
Yes.
I mean, that's basically all we're doing, because we're just saying you, at each step, you shovel in all the stuff and you do all these, whatever it is, n squared different comparisons or something between these different players, if I'm not mistaken, and then we get out some new state. Is that right?
Yes, so the game history will build up gradually, and always that game history will be fed with these behavior strategies. Yes.
Right, but is it correct that if you have n players, you've got, is it correct to, if it isn't a cooperative game of some kind, that you've got n squared different individual comparisons to make? Is that right or not?
No, I mean in every step, but then you have an infinite possibility for behavior strategy.
Oh, but am I right that at every step you're playing one against one? Is that right? Or are you playing one against all?
No, this can be generalized. So in this prisoner's dilemma, one against one, but in the general case, it's perfectly well defined that n players are playing the game.
I see. So in other words, what you're saying is that.
But you can have different ways of specifying how they play, right? And it can be that each person plays once against each of the other players every round, or you can have them randomly paired, or you can have them laid out in space. There's all kinds of ways you can do population dynamics on it. The simplest case is just where there's two playing each other iterated.
Yes. So similarly, as in replicator dynamics, this population grouping can vary. Yes.
But also in this case, whereas replicator dynamics is an ODE, in this case, this is an iterated function, correct?
Basically, yes. Yes.
I mean, presumably there's a version of this.
The complication is that it's an iterated function, but the move vector that you're taking in to decide your next move is a growing length list.
I understand.
And you can have strategies to only look back a certain distance, but if they're not finite look back ones, then the complexity of the input thing gets larger and larger.
Yes.
Yes, obviously, right. I mean, it's just a function that takes a list, basically. Or in general, in a continuous case, it could take an interpolating function, I would assume.
Yes, and in a many player thing, take a whole set of move vectors, right? It could have a move matrix for all the past moves, all the other players.
Right, but each one is separate, right? I mean, in other words, it's the succession of states of the game. It's the time series, effectively, of states of the game, where at each time step, you know what each player did.
Yes.
Correct? So, but each player, the only place where those interact is at the current time. You are looking at that whole history under the current state, and you're deciding on the basis of that what your next step is going to be.
Yes.
But in general, and this is where I suppose it gets kind of complicated. I mean, I don't know, I'm sure somebody has done this fanciness. You must be able to have some integral differential equation that looks back at the complete time series and then says, based on that, it applies some, I mean, because the differential case is an instantaneous state of the game and what the instantaneous next move is. But if you're going to take account of infinite history, I would assume that there's some integral that you take over the infinite history with some appropriate kernel and so on. Yes. And that must be the simplest case of that you described, the Markov type thing, is like that's the discretized version of that, where there would be some, finite kernel support going back some number of steps.
Yes, it would be an integral equation, basically.
Right.
If you want to make it a differential, so if you want to make a infinitesimal version of this.
Do people do that, or is that like still in the future?
Well, I'm not aware of that, but
okay. I mean, because you also have to parameterize. I mean, the difficulty here is that parameterizing algorithms is a tough business. I mean, people.
Yeah, the usual parameterization used here is to start from the shortest look back strategies and then go to longer look back strategies, and that way you can have a natural way of counting through them in terms of their complexity, and then you can arrive at theorems like if I've got a longer look back than the person I'm playing against, then if the game goes on long enough, I can learn his whole I can learn his input output tree and predict his moves and so forth. But that's the typical way it's parameterized. It's just what are the allowed look back lengths and how do they vary across the players. That's the typical way people go through this. If you allow infinite look back both for all players, then you're right. It's incredibly complicated and you can't tell which strategy you're talking about.
Mm-hmm. Okay, but I mean, in that case, really, it is just a packaging of nest lists that we're talking about here.
Yes.
Actually, it's not even that. It's the. Sorry, it's the thing. What do we have? We have. I mean, for example, nest while list allows you to say how far back you want to look to determine a test, for example.
Yeah, when we've done like NKS summer school projects about this sort of stuff, people have just built it out of nest list and had different ways of the complexity comes from how they want to, as you say, enumerate all the strategies and how far they want to push in the strategy set to look at all the different possible combinations. But the underlying evolving function is just a variant of nest list with appropriate logical arguments set up for it.
Okay, fine. But so again, I just want to understand the distinction here, because this is the discrete case, and then which is, but then the replicator dynamics is the continuum analog of this for certain simple strategies, correct?
Yes, so I think here the main invention that you can use behavioral strategies. In the replicator dynamics, usually the strategies are not looking back or not taking into consideration.
I understand, they're just the instantaneous state.
Yes.
They're taking a derivative as opposed to some integral differential, some integral kernel that looks back some, I mean, this would be the analog, I don't know, there must be in control theory, there must be a similar kind of thing. Roger, how does that work? Where you look back, where you either know the instantaneous state of the system or you also know the history.
Yeah. So often the way you formulate it is some kind of goal. So it's like some integral, for instance, or sum that you want to minimize or maximize. And then you have constraints for how the system needs to evolve. Like you can't, it has to follow Newton's dynamics or something. So there are constraints, differential constraints.
But
Then
this
you
question,
then you
Go ahead.
compute the optimal control that maximizes or minimizes that goal, that integral. And so
Okay.
for simple cases, we already have it. In the general case, this leads to, you can compute it in the general case. Richard Bellman and so on shows how you can do that with dynamic programming, dynamic optimization, but it has a cursive dimensionality problem.
So how does that relate to finding optimal strategies here?
It's the same cursive dimensionality, probably.
No, but is it the same problem, though?
I think it is, but I need to dig in deeper.
Okay, all right, but fine.
I think that all these three things that we bring up, control, optimal control, iterated games, and reinforcement learning are variants of the same perspectives onto the same kind of problem.
Right. So for us, though, the thing that will be really nice is, install a PID controller or something in this game, whatever that might mean.
Yeah.
And I think in economics, people do think in that kind of way.
Also, by the way, so here's a very, very elementary way that I can describe what you were just saying, how to look back. So PID is the oldest, simplest possible controller that you could imagine. Mm-hmm. It's pretty dumb, but it's not too bad either. So it has PID means proportional to the error. I means integral, so that's integration of the error, and D means derivative. And so that integral, it keeps track of, how much deficit that you've aggregated up. Mm-hmm. And it will zero that out eventually, but it keeps track of that integral.
Right. So that's an analog of a continuous version of this iterated game.
Yes. But
with a one player, that's effectively a one player game playing against nature or something.
Yes.
But you could imagine.
Yeah, that's right. And in these iterated games, part of the interest is, can you use past game history to infer the other person's strategy and therefore, be able to predict it better. And that's what the longer look back things can effectively wind up doing that you can't quite do in the nature case. Maybe you can.
A PID controller, its integral goes back to the beginning of time. Is that true?
Yes.
I see. So
but that's trivial to represent as a state. Do you see what I'm saying? You don't actually compute it.
No, I understand. You just accumulate the integral. You accumulate the error.
Yeah.
But presumably you could have two PID controllers playing against each other. Isn't that what happened? I'm trying to remember. There's a famous story about Edison and the time when he was trying to first get the electric, two electrical generators, and they were connected in some way, and they repelled in phase, and one of them eventually blew up. And then,
I haven't heard that story, but that's very true. So you often have, this can happen today too. You have like multiple on a ship, for instance. You can have multiple engines, and the question is, how do you coordinate them? Mm-hmm. Yes, there are plenty of I've heard plenty of stories where they more or less kind of burn each other out.
But so is that not the continuous analog of games against controllers?
Don't know.
I think it must be something very similar, right? Because it's at each point. Well, okay. But for us, the main point is to make compatibility between these at least three different views of the same type of problem.
Yeah. The goals and the audiences are slightly different, but yeah, there should definitely be bridges. Absolutely.
Right. Because
but if we unify it, we might make a product that nobody wants to use.
Oh, I agree. So. I agree. But the issue is, how do you take a PID controller and stick it in an economic game theory thing? How do you take
but economists are I've sort of shown the way there. They use a lot of control theory, actually.
I know, yeah, I know. But I mean, the question then is, how do we make sure that our control theory functionality slots into our game theory functionality?
Right. Yep.
And the neural net similarly,
Yep.
Because again, I suppose the question then, I mean, so various ways round. One is to use a neural net to learn some iterated game, which should be possible as now that we're working on sequence prediction and so on, you should be able to just plug sequence predict into one of these iterated games. In other words, sequence predict should be the function that is fed to say, what should you do next? Since sequence predict will take a sequence as input, well, it takes a collection of historical sequences. Yeah, I'm not sure how that should work. Go ahead.
The interesting point is that it's better if you don't optimize always for the next step or for the present, but you also try to figure out what would be a nice time horizon. I mean, in some of these
sounds like corporate strategy. Okay, yes, go ahead, please.
So the thing is that the strategies which enforce the other player to cooperate, for example, are better off. Naturally, in every instance, the better would be to find a place where they can defect. But if they, there is a story that if you start this prisoner's dilemma, for example, in the beginning, the defectors are winning, and then gradually these tit for tat strategies are somehow cleaning up the players, and then after a transient period, cooperation starts to be more rewarding.
Mm-hmm. We have run out of time here. This was very interesting. There's a question for Pakinji about apply a PID tuning method to a game like the Ziegler-Nichols method. I don't know if anybody here knows what that is.
That's it's in our PID tune function. It's a method to automatically tune the parameters of a PID. So you have the world, the plant, and you automatically derive what's a good controller.
I do wonder. I don't think that our machine learning team and people working on sequence predict have probably ever even heard of a PID controller. But is it obvious that PID control shouldn't be, and things like that shouldn't be possible methods for sequence predict? That might even work better than some of these fancy neural net things?
Yeah, I mean, we should look at it. But I mean, there are already a very standard predictors like Kalman filters is, kind of the standard predictor used in control theory and derived there.
I understand, but I don't know whether the Kalman filter approach has been ported to, okay, look, it's the same type of thing as, is it really just logistic regression or is it fancy, neural networks?
Right, exactly.
Right. And this is the same type of thing. I have no idea. And it could very well be that our sequence predict function would just get better if we were to put in some.
But you're hitting all the things that I'm planning for us to focus in on.
Okay, fine. Good. Well, that's good. All right. Well, so it seems like we have a nice extra leg to that with Joseph's work here on game theory.
Yeah.
And it's very, very promising. Okay, we had a bunch of questions and comments on our live stream. I suppose I should just look at them for a second. Ethan is pointing us to a game theory library, which we should look at. Comments about applicability to reliability engineering.
What did it say about reliability?
I know that in reliability stuff, people often treat those as game theories where they imagine, the worst case scenario is like you're playing against a hostile nature who can make strategic moves against you to break your systems. So they use a game theory context to look at reliability because instead of thinking that nature is going to act randomly, you think that nature is going to act strategically, and that it sort of gives you something which is stress test to worst case.
I see. Sounds like a pretty good idea.
this can be very naturally implemented in this game transform, where you could assume that the opponent's payoff is, for example, minus is the opposite of your payoff, and then you can also transform utilities to regrets, which is a better setup if you are thinking that the nature is a malicious opponent.
But that's interesting, Joseph. But the thing is, what Stephen would say next, or if he's timed out now, but is we have a whole big framework for reliability of systems, and the question is, can it plug in there somehow?
Of course.
Right. Yeah, a comment here from Sun on the live stream about neural nets might achieve the same as things like PID controllers, but they don't explicitly integrate. And that's true. I mean, neural nets are, in some ways, they're a lower level and therefore more generic approach. But the place where you put all the trickery in is in the encoding functions and so on. And I could certainly imagine, actually, this is an interesting idea. Okay, so we have the notion of a net encoder, right? Question is, what is a net encoder for a sequence? Well, one obvious net encoder, which I'm sure we do not have, is a net encoder that integrates, right? In other words, you feed in the classical, Kalman filter-ish kinds of things or PID kinds of things by basically putting them in a net encoder, then letting the neural net operate on the features that are generated from, after you've already used that kind of classical methodology. That's probably something worth looking at. I mean, the fact is that our sequence predictor right now is pretty bad. Our classify and predict functions are quite good. And, you feed in things that you think might work, and they typically work better than you expect. Whereas sequence prediction has, we really don't do that well on sequence prediction. Not that anybody does, but it might be that these, if we could put in these classical methods as encoders, that might be very helpful. Okay, I need to go. Good stuff, guys. And thanks to folks on the live stream also. Till the next time.